Hi all together. This is the lecture on 3D coordinate systems. This time we will talk about a special representation of rotations, namely by quaternions, which are 4 vectors. And we will discuss how to concatenate rotations if they are given by some parameters, not by the full rotation matrix. So let's start. The motivation is very clear. We started with rotation matrices. Rotation matrices contain 9 numbers and we have 6 constraints, so we have a highly redundant representation. There are no cosines and sines in it. But the other less constrained representations, Euler angles or axis and angle, have 3 or 4 parameters, but they contain trigonometric terms. So the question is there a representation which has not so many parameters, but can do without any trigonometric terms? And there exists one, and this is exactly what we will talk about it. The nice thing about it, it is an interpretable representation, and it's unique except for the sign. So let's start. What are quaternions? Quaternions are 4 vectors, as you see here. Q is a 4-vector Q0, Q1, Q2, Q3. You could also say it's a pair of a scalar and a vector. So of course the scalar Q0 and the scalar Q here are the same, and the vector Q consists of these 3 parts. And there's an interesting third representation with hypercomplex numbers. You remember the complex numbers with the imaginary unit I, where we assume that I square is -1. So here you have a representation of a quaternion being the sum of Q0, 1, and 2, and 3, and the 1, 2, 3 indices are multiplied with I, j, and k. And the convention is that I square is -1, j square is -1, k square is -1, and we have the multiplication rule I times j times k is -1. We will look into this a little bit more detail, but we will not use the hypercomplex numbers for the whole lecture. So there are of course special quaternions. So there's a 1 quaternion, which corresponds to the 1 in real numbers. So it's either the 1 here, or 1 without vector part, or just the unit vector E1 in 4D. Then there's a unit quaternion which has length 1. That means here we have the length of the quaternion is 1, or the sum of the squares of the scalar part plus the square of the norm of the vector part is 1, or just the sum of these 4 squares is 1. And similar to the complex numbers, we have a conjugate quaternion where we just negate the vector part. And then there is a pure or vector quaternion where the scalar part is 0. So if we have a vector Q, we can extend it to a quaternion by just adding a 0 here, or putting a 0 at the first part, or we just have this hypercomplex number with just I, j, and k as basis vectors. Now, the interesting thing about quaternions is that they build an algebra, as you know it from real numbers with addition and multiplication and division, and also for complex numbers, and this also holds for quaternions. So we start with the addition, which is very simple. So we have 2 quaternions, Q and R. We add them by adding the individual components. So P is Q plus R, etc. And we have it, of course, here for the vector, as you would expect. And of course we have it also if we have this in this hypercomplex form. So this is the easy part. So what is the product of a quaternion Q and a quaternion R? This gives a new quaternion P. And the scalar part of this new product is the product of the 2 scalars minus the dot product of the 2 vectors. And the vector part is the sum of the 2 vectors weighted with the other scalar part plus the cross product of Q and R. And you see here, if we exchange Q and R we get here a negative sign, so it's clear that if we exchange the two factors, we will not get the same result. Now, what does that mean if we write down this in vectors? So we have here the resulting 4 vector, and the result of each individual element is written down in this vector explicitly. So the first part is the product of the two scalars. So this corresponds to this one. And then we see here minus the scalar product of the two vectors. And then we see the multiplication of r with q. So r corresponds here to r0. So we have here r0, r0, r0 multiplied with q. We have q times the vector r, which is here on the diagonal. And we have the cross product of q and r, which are these off-diagonal terms if we look at this as a matrix. So we have here minus q1, q2, 1, 2, 3, 2, 3, and 3, 2. And the same here in opposite sign. So we will see that this can be written down as a matrix vector product, but you find this expression here, here again in this full expression. Now, I don't want to work out the case for the hypercomplex numbers, but one can prove that if you have these relations, these 4 relations, that the squares of the bases I, j, and k are minus 1, and the product of I, j, k is minus 1, then you can show that I, j is minus ji and identical to k. And if you use this, you come to the same result as written down here. I don't want to work this out. Now the question is, how does somebody come to such an idea to do this? It was Sir William Hamilton in the 19th century. He had the goal to integrate the scalar and the vector product into a common product. So look what we had here. So we had here the scalar product and here the vector product. So if the scalar part q and r both are 0, we are left with this dot product, negative, and the cross product. So he succeeded in doing this. And then on a walk in 1843 with his mother, he come to the idea to write down this with hypercomplex numbers, as we saw it this way. And there's a table at this place where you can find this invention documented. So let's go and look a little bit more detail into the structure of the multiplication. The multiplication of two quaternions obviously is bilinear in both components. So you see here only products of q and r without any squares. That means if you take out the r here, you are left with q0 minus q1 minus q2 minus q3. So you can write this down as a matrix vector product. So this matrix has exactly the structure of this vector, these coefficients of r in here. And you see it has q here, and here the diagonal terms, qi3. Here the vector part, q. Here the negative vector part. And here on the off-diagonal elements, the skew-symmetric vector, the skew-symmetric matrix of the vector q. So you have a very nice structure for this multiplication. You can actually do this easily in MATLAB by building such a matrix and multiplying it with the corresponding vector. Now, sometimes we would like to write this down as a function of q. Yeah, this is also linear in q. We can do this. So we just take all these q's put them in here and multiply it with some other matrix, which I call T bar. It depends on the quaternion elements R. And if we compare the coefficients, we find here R0, R1, R2, R3, which is here. And then we see here the negative values of R, which is R1, R2, R3. And we again see here the cross product terms. So actually the matrix looks nearly the same as this one. So you see here plus, minus, 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 plus the vector. On the diagonals are the scalar parts, but this q-symmetric part has opposite sign. So we have here the classical plus SQ, and here we have minus SR. So the two matrices are not transposed of each other, but they differ just in this skew part. That's the reason why the multiplication cannot be commuted, because these matrices are not the same. So we have a look at these matrices later. And first we have a look what is a inverse quaternion. An inverse quaternion is defined as the conjugate of the quaternion divided by the norm square. So the conjugate quaternion is scalar part minus the vector part. And the quadratic norm of a vector is nothing else than the sum of all these values. So you can easily prove that if you multiply q bar with q power minus 1, you will get the norm of the vector. The properties of these multiplication matrices are quite interesting. So if you have the multiplication matrix of the inverse of a quaternion, you actually obtain the inverse of the matrix of Q. If you take the conjugate quaternion, this corresponds to the transposed matrix. So if you take the T of Q bar, you get actually the TQ transposed. And moreover, if we have unit quaternions, let's say E is Q divided by its length, then we can see that these matrices T and T bar actually are orthogonal matrices. So this is quite interesting, and we might use this later in some derivations. Now, why do I tell this all? Because there is a very close relation between quaternions and rotations. So we can explicitly represent rotations using quaternions. So let's assume we have the following task. We have a point P with coordinates vector P. We have a rotation axis R and an angle theta. And we want to rotate the point to P prime with coordinates P prime. Now the solution is in principle simple, but we have to prove that this is okay. So we have to choose an adequate quaternion P as a function of the vector. Then we have to choose an adequate quaternion which depends on R and theta. And then we have to do a double multiplication with P of P, with Q from the left and Q inverse from the right. And then we get a new quaternion P prime. And then we have to derive P prime from this quaternion. So this is a program. And now let's have a look first at what this double multiplication does. So the double multiplication is Q from the left and Q power minus 1 from the right. So we have P prime is 1 over Q square multiplied with Q bar, because Q bar divided by Q absolute value square is the inverse. So we have to multiply Q with P and the conjugate of Q. Now we apply our rules with our matrices. So we have this vector, and we have to multiply Q with this quaternion, which is the multiplication matrix TQ multiplied with this expression. And this expression is the multiplication of P with Q bar. Now we would like to have the P on the other side. That means we have to use the multiplication matrix T bar of Q bar multiplied with P. And if we now leave out the brackets and write it out, we get the following expression: 1 over Q norm square multiplied with the T matrix of Q, which is Q, negative vector, positive vector, Q times the unit matrix plus the skew symmetric matrix. And then we have the T bar of Q bar. Now, the T of the T bar of Q would be Q minus Q plus Q, Qi minus SQ. And because the vector parts are negative, because we have the matrix of Q bar, not of Q, we have to take the negative values. So we get here plus Q and here minus Q, and we get here plus SQ. Now, okay, we have to multiply these two matrices. And if we do this, we get, for instance, Q square plus the length square of Q. Where this is here. Then we have to multiply Q, the scalar part, with the vector part, Q transposed, which is this one. And then we have to multiply minus the vector part transposed with Q, which is Q times Q transposed, multiplied with the unit matrix, which of course is not necessary, plus the product of Q transposed, which is a 3 vector multiplied with the skew symmetric matrix of the same vector. So this is the cross product of Q and Q, which is 0, so we don't have to follow this term. And now you see that because we don't need this I, this difference vanishes. And we are left with 1 here, 0 here, 0 here, and this expression divided by the norm square of Q, multiplied with our quaternion P, scalar part, vector part P. So the scalar part doesn't change because we have a 1 here. And the vector part is nothing else than the multiplication of this vector multiplied with this matrix. So we see here a dyadic product of Q, we see here a unit matrix, and we see here a skew symmetric matrix. And if we now simplify this expression, we get a rotation matrix. At least this is what the claim is. So the claim is that this expression here is a rotation matrix. We have not proved this up to now. So if we work this out, we get here 1 over the norm square. And then we have here 3 by 3 expressions, which again are not so easy to remember, but also not so complicated. So we start here with Q0 positive, Q0 square positive, Q0 positive. Then we see here Q1 positive square, Q2 square positive, Q2 3 square positive. The other two elements are negative. 2, 3, 1, 3, 1, 2. So these are the diagonal terms. The off-diagonal terms are 2 times the difference of 2 products. The first product is actually nothing else than, if you have here the index 1, 2, the product of the elements Q1 and Q2. Here 1, 3, here 2, 3, here 3, 1, etc. So the first part is just nothing else than the dyadic product. And the second part is nothing else than the Q0 multiplied with Q1 negative, Q2 positive, Q3 negative. That means here we see the skew symmetric matrix in here. So after some time you might be able to remember this. So this is what we would like to prove, that this is actually a rotation matrix, and we would like to know how to interpret the values scalar q and the vector q. Now have a look. This rotation matrix is a sum of some factor scalar multiplied with a unit matrix, a factor multiplied with a dyadic product of a vector, and a factor multiplied with a skew-symmetric matrix. This may be comparable to the representation of the rotation matrix which we learned last time, based on a rotation axis and a vector and a rotation angle. So we would like to compare this matrix with the entries I3, DQ and SQ with the rotation matrix based on rotation direction and angle, which also depends on I3, D and S. So the first thing is that we have to have a guarantee that the coefficients are the same. So if we clarify, we have to see that, we make it simple. We assume that we have a unit quaternion. So we neglect this part. And then Q, the scalar part squared minus the dot product, should be the same as cosine theta. Second, the 2 times the dyadic product of Q should be 1 minus cosine theta multiplied with the dyadic product of R and R transposed. And finally, this skew-symmetric part, 2 times the scalar part multiplied with the skew-symmetric matrix of Q, should be the same as sine theta multiplied with the skew-symmetric matrix of the direction vector. So we have 3 constraints, and they need to be fulfilled to be that these 2 matrices are the same. And we should be able, hopefully, to derive what is Q, the scalar, and the vector Q as a function of R and theta. So let's do this. So the first thing is that we observe that because we have here a skew-symmetric matrix here of Q, here of R, these 2 vectors should be parallel. So we say the vector Q must be some up to now unknown factor f multiplied with R. If we take the length of these vectors, we get the length of Q is f squared. Now we use this result and look into the first condition. So we need to see that cosine theta needs to be scalar part minus the length of the vector square. That means the cosine of the rotation angle should be Q square minus F square. The third constraint says the sine of theta should be 2 times Q multiplied, the difference between SR and SQ is the factor F, so it should be 2 times Q times F, which stands here. Okay, now we have to solve this equation. If you now remember your trigonometric knowledge from the first year in higher mathematics, you find that you have learned the cosine and sine of the double angle. The cosine of the double angle is cosine square minus sine square, and the sine of the double angle is the product of cosine and sine multiplied with 2. So if we compare this, we see that the Q should be the cosine of theta half, and F should be sine of the half angle theta. So we have solved the Q and the F, and used only two of these three equations. So we have to be sure that also the third equation is fine. So what we didn't use is this equation. So this is 1 minus cosine theta is r transposed, and this is 2 times f square. So we have here 1 minus cosine is 2 times f square, and this is 2 times sine theta divided by 2, which is fine. Yeah. So actually all three constraints are fulfilled, and we can represent q and f, express them as a function of theta. And we know that if we know f, we also know q, because we just have to multiply our rotation axis with f, which is sine of theta half. Okay, put this together. We said we need to choose an adequate quaternion. So let's choose the quaternion cosine theta half and sine theta half multiplied with the rotation direction, or cosine theta half multiplied with the unit vector plus sine theta half multiplied with the scalar 0 and the vector being the rotation axis. And you see this is a unit quaternion, because if this vector has length 1, this vector has length 1, and cosine and sine square sum to 1. And this means the quaternion which does actually the rotation using can be interpreted, namely that the first, the scalar part, is cosine of the half the rotation angle, and the vector part is the direction of the rotation multiplied with sine of the half of theta. Moreover, which we didn't discuss up to now, is that if you look at this equation, if you multiply q with some scalar mu, then you get all elements here appear in squares. That means you here multiply this expression by mu square and divide by the norm of the vector, which is mu square divided, so it doesn't change. So actually, if we treat quaternions for representing rotations, quaternions are 4 vectors which are homogeneous. You remember, an entity is homogeneous if multiplication with an arbitrary factor, not 0, doesn't change the entity. The entity is a rotation, so if you multiply the q with some arbitrary factor, it doesn't change the rotation. So whether we work with a unit vector or with an arbitrary vector, it doesn't matter. So if q is 1, that means we assume a unit quaternion, then we of course can simplify the whole expression and get this matrix. I don't want to discuss this more in detail. You just see that this depends on the unit matrix, linearly on SQ and quadratic on SQ. So it's similar to the other representation which we have seen for the representation with rotation axis and angle, where it depends on the skew-symmetric matrix and its square. What we see here, it's bilinear in all elements of Q, and of course we have a quadratic constraint. We have no trigonometric terms in none of these representations. So this is exactly what we wanted to achieve. Now what we have seen is that we can represent rotations with unit quaternions. Now what does this mean geometrically? We see that unit quaternions are unit 4 vectors. That means that they are unit vectors in a 4-dimensional space. That means if we go back 2 dimensions, we have the unit vectors in 2D, and they build the circle. So the circle S2, S1 in the plane contains all unit vectors of length 2. So we have here, so to say, the sphere S1. And we have a sphere S2, the classical sphere. The upper index 2 means we have a two-dimensional surface in R3. And it's represented by all 3 vectors which have unit length. This sphere. And now we just go 1 dimension higher. That means we have a 3 sphere, not a 2 sphere, S3, in 4 dimensions. We cannot imagine how this looks like, but this is the idea that we have a generalization of the circle, the 2D sphere, to a 3 sphere. The main thing why I discuss this is that you see here the circle and the sphere have no boundary. That means there is no place where you don't have any values close to some value. If you have a unit vector from here to here, there are unit vectors close to it. If you have a unit vector here, you have unit vectors around at that point. That's the same in 3D. That means if you have a unit vector in 4D, which represents a rotation, you have unit vectors close to it. That means you have rotations close to it. And there is no boundary. So we will not have a discontinuity, which is very important. And we have no singularity. There is no case where the representation breaks down. The only thing which is left is that we have a sign ambiguity. So we said for arbitrary mu, you can multiply q with that factor. And here, of course, if it is a unit quaternion, you only can change the sign. So this is the only ambiguity for unit quaternions which we have to take into account if we estimate quaternions. Let's look at some examples. You remember this rotation matrix with the 1s on the 1, 2 on these places. And this rotation corresponds to the quaternion half of -1, 1, 1, 1. So it's a rotation by arcus cosine of -1/2 multiplied with 2. So arcus cosine of -1/2 is 120 degrees. That means we have a rotation by 240 degrees. That means negative rotation about 120 degrees about this axis 1, 1, 1. And this matrix, which we remember is a rotation around the x-axis by 180 degrees. This corresponds to this quaternion. You see this is the second unit vector. So you have here 0. The arcus cosine of 0 is 90 degrees. So the rotation is by 180 degrees. And we see here the rotation axis 1, 0, 0. So it's easy to interpret these elements in these quaternions in terms of rotation axis and angle. I want to make a third example, which goes back into the plane. In the plane, we said the rotation is represented by one angle. And we need to represent the matrix by cosine and sines. Is there also a representation which doesn't use trigonometric terms? Yes, there is. So let's assume you have a vector, a 2-vector A, and you have a look at this matrix, which is AA minus B, divided by the length. Now, let's assume A square plus B square is 1, which is a unit vector. Then we have here the cosine minus sine plus sine. So this looks reasonable. We can represent this as 1 over the length, there should be a square, multiplied with the sum of A times the unit matrix plus B times a skew-symmetric matrix in 1D. So this is this skew-symmetric matrix. So this would be a representation of a rotation in 2D using a 2-vector AB. And we remember that the rotation in 2D is a rotation around the z-axis in 3D. So this rotation corresponds to a rotation in 3D with some q0, which only defines the angle, and the axis 0, 0, q3. So you see here this is the rotation around the z-axis. Okay, there are some questions which I just want to pose. How is the relation between these scalars AB and q0 and q3? So how is the relation between these rotation in 2D and the rotation in 3D? Then try out what happens with squaring S1, this matrix. And then compare the rotation which we wrote down here with the rotation if you represent points in the plane using complex numbers. You remember that if you multiply a point, a complex number, with another one, you have a rotation and scaling. So if r is a unit vector, a unit complex number with a length 1, then you get a pure rotation. So have a look how this relates to this representation. Okay, now I want to go back and ask, are there other representations than those with quaternions which not use 4 parameters but only 3? And there are 2 of them which are interesting. One is proposed by Rodriguez in 1840, and he proposed to use a 3-vector M and use the quaternion normalized to 1 here, and the vector part is 1/2 of M. It corresponds to the equivalent to the quaternion 1, and tangents of half the angle multiplied with r, because we usually have here cosine and sine. So if we divide the quaternion by cosine, half of the angle, we get here 1, and we get here the tangents. So these 2 quaternions are the same, and m actually, half of m is this expression. Now we see, of course, if theta is 90 degrees, the tangent is infinite. So this representation doesn't work for angles of 180 degrees, which may be a disadvantage if you have such angles in your application. For this factor 1/2, let's have a discussion later. And if you write this out, we have a rotation matrix with this vector ABC. Then this matrix again is similarly structured as that with the quaternions, of course. And we have here scalars 4 and products of 2 of these elements, A, B, and C. And we have, instead of the norm, we have here 4 plus A square, B square, C square. So this is very similar. And of course, if we have the vector M given, it's easy to get the rotation angle, rotation axis, which is just normalizing M, and we get the angle from the arcus tangens of 1/2 of the absolute value of M. The second representation is the Cayley representation. He said, okay, let's take the quaternion Q, just 1, and a vector U. Of course, the U is the same as before. The difference to the Rodriguez is just a factor 1/2 at this place. Now you can show easily, if you take the quaternion representation here for this rotation and plug it into the definition of the rotation matrix, depending on quaternions, and multiply it with unit matrix minus the skew-symmetric matrix of U, short 1 minus S, you get actually 1 plus S. And in a similar manner, you can multiply from the left and get the same expression. So if you now solve for RQ, you get a representation of the rotation matrix depending only on u, which is the Cayley representation. And this is I plus s divided by I minus s. And you can also take the inverse from the left side. So you have here the same matrix R in Cayley form, depending on u, is 1 minus the skew-symmetric matrix inverse multiplied with unit matrix plus skew-symmetric matrix. So this is very interesting because it's just the division of two matrices. Now, there's a general relation which you don't need to remember. This is what is called the Cayley transformation. If you have an arbitrary n by n matrix where no eigenvalue is -1, then the Cayley transformation of this matrix is this expression. So you see we have here 1 minus a and 1 plus a and the inverse. And the interesting thing is that the inverse transformation has exactly the same structure. So if you plug in now b here, you actually come back to a. And then he showed that if A is a skew-symmetric matrix, then B is a rotation matrix. This is very interesting. So he showed this in a general way. There are alternative definitions, which I just want to mention here at this place. That's the reason why I wrote down here that this is the Cayley transformation of minus SU, because we have here I minus S divided by I plus S. Here, this one. Now, why is the Cayley transformation interesting? Let's make an example. We can apply it to the following problem. Let's assume we have I points, here in this case 4, on the sphere, and they are related by rotation. So actually you see the points move on small circles. So we have a rotation axis and we have a negative rotation. So once more, just to see this, so we have here 3 points in front of the sphere, and we have here 1 point in the back of the sphere. And the question is now, given these pairs of points before and after the rotation, how can we determine the rotation? And I show you a direct non-iterative least square solution. We will discuss this problem, rotations from point pairs, later more extensively with 1, 2, and 3 points. So we use Cayley's representation and start from the basic relation. So we take the point xi, multiply it with the rotation matrix, which is this one, and get the point yi. Now here's the inverse. We put this matrix on the other side and get 1 minus the skew-symmetric matrix of u multiplied with y is equal to 1 plus the skew-symmetric matrix of u multiplied with xi. Now what you see here, the skew-symmetric matrix contains the 3 unknown parameters for the rotation in linear form. So this is a linear equation in u. So let's rearrange the terms. We start with x here, which is I times x, which is this one. I times y on this side. On the other side we get minus yi. And then we take the cross product of u and x and reverse it and get minus x cross y. Put it on the other side, we get this skew-symmetric matrix of x. The same here, we have here the cross product of u and y. If we exchange the two factors, we get the negative value, so plus y cross u, which is the skew-symmetric matrix of y multiplied with u. So we have here some coefficients multiplied with u gives some vector on the right-hand side. for each individual point. And if we now plug all these left factors into a big matrix A, and all the three vectors on the right-hand side in a large vector B, we get a linear equation system A times U equals B. So the A matrix consists of all these sums of the skew-symmetric matrices. It's a 3 times I matrix because these are 3 by 3 matrices, and it has 3 columns. And the vector has, of course, length 3i because each of these individual vectors has length 3. So we have to solve this equation system with a tall matrix A, and because we usually have some errors in our measurements, we look for the least square solution. So we minimize the difference between A, U, and B, and get what you know from least squares theory, this expression, explicitly to get U from this linear equation system. And if we now know U, we can plug it into our representation using the Cayley form and get our estimated rotation. Of course, this is an approximation because we don't take into account any uncertainties of X or Y. But this shows that it is very useful to have this Cayley representation for making such a manipulation which leads from a highly nonlinear representation to a linear representation. Okay, this closes the chapter on quaternions. We have seen we have 3 representations with the quaternions themselves and with some special quaternions with only 3 parameters. And now we want to look into concatenations of rotations if these rotations are represented by parameters. So in general we have the concatenation of 2 rotation matrices, R prime and R double prime, just by the product of these 2 rotation matrices. So of course this is simple. This is what we did last time already. Now let's assume we have R prime and R double prime represented by some parameters P prime and P double prime. So these are not coordinates now, these are parameters. Now how do the parameters of R, P, depend on P prime and P double prime? So let's assume we have Euler angles. So we have rotation depending on alpha, beta, gamma prime, multiplied with the rotation depending on alpha, beta, gamma double prime. We multiply these rotation matrices, we get a rotation matrix, which depends on some parameters alpha, beta, gamma, which we would like to know. And the question is there a simple function, f of the given 6 parameters? No, it doesn't exist. It's not a simple function. You can write it down, but it's very awkward. But such an equation for the parameters of the combined rotation exist for the quaternions and of course then for the Rodriguez and the Cayley representations. So the first thing is that we look at the concatenations of rotations if we use quaternions. So let's start with the first rotation of some point P with the quaternion Q prime. So we have to multiply from the left with Q prime and with Q prime inverse from the right-hand side. We get the transformed point P. Now we have P being the point and Q being the quaternions. Now we apply the second rotation with some quaternion Q double prime. So we get the rotated point P double prime is the first rotated point P prime, left and right multiplied with Q double prime minus 1. And if we plug in this, we get this expression. So we get Q double prime, Q prime. And from the right, we get Q prime minus 1, Q double prime minus 1. And if we take brackets, we get here Q double prime, Q prime. And we can write this expression also as Q prime, Q double prime inverse. Aha, that means the concatenation of the rotation is nothing else than the multiplication of the corresponding quaternions. So if we multiply two rotations which depend on q prime and q double prime, we get a rotation which depends on q, and q is nothing else than the quaternion product of q prime and q double prime. You see, the sequence of the order of the multiplication is the same. So we have an explicit expression for our new quaternion, namely depending on our first and second elements of the quaternions. So, of course, this then specializes to Rodriguez. So let's assume we have m prime and m double prime, being ABC prime and ABC double prime. There should be no transposed. Then we can directly specialize these equations to these ones. These are quite simple. So the new vector m of the combined rotation depends on ABC, 1 over some product, sum of products, and some easy concatenation. So the sum of the elements A, B, C, and there is a cross product, obviously. And the same for the Cayley form. So we have here u prime and u double prime with the corresponding elements. Again, this t should not be there. And we get the parameter vector u of the combined rotation of the Cayley representation ABC in this form. So this is very simple to derive from the previous one and shows that there is a simple concatenation rule for representations of rotations with quaternions or in the special form of Rodriguez and Cayley. So what did we discuss this lecture? We talked about quaternions. There are 4 vectors. They build an algebra. That means we can add, we can multiply, we can have brackets, we have a distribution law, and we have an inverse element, we have a unit element. So it's, as we know from classical algebra, except that the multiplication is not commutative. Then we have seen that the quaternions can represent rotations. This representation is purely rational, so there are only fractions of bilinear forms. So we have no trigonometric forms in there, and which eases, of course, the calculation and, of course, speeds up the computation, because cosines and sines, of course, always take more time than just polynomials. The space of rotations, that means of the unit quaternions, is the 3-sphere, which is continuous, which has no borders, which is nice for the estimation. And the good thing is that we have an interpretation, because there's a very close relation to the axis and the angular representation. The vector part of the quaternion is the direction of our rotation, and the angle can easily be calculated. And we have some special forms, which only 3 parameters, which only work for angles which are not 180 degrees. The Rodriguez and the Cayley representation, and we have seen some advantages of these representations. Especially all these representations can be easily concatenated based on their representation. Thank you very much. The next time we will talk about small and uncertain rotations. And then we will have a look at the relations between these many, in brackets 7, representations of rotations. And then we have a look at rotations from point pairs. We have seen a general case, but there are also some special cases which are very useful. Thank you very much. Until next time.